Hello, Chem 30. Welcome to our 7th week of distance learning and getting into the routine of this, to be sure. We are in the last week of our organic chemistry unit. So starting next week, we're into the 4th and final unit of this semester, which is kind of crazy. And in this last week of organic chemistry, our focus is on some different reaction types. Now, if we were in class, we would have started this section with quite a long discussion about the oil industry and about the utilization of a variety of hydrocarbons within the oil industry and the importance and impact of it. So that being said, unfortunately, it is an area that we've decided to leave out with the material we need to condense to do this in this format at home. But I really encourage you to look into the risks, the benefits, the contribution to society of the different hydrocarbons. It's quite an interesting area, and certainly there's a lot of things from an industry perspective and from a future perspective that you could look into going into, especially imagine looking into biodegradable plastics, right? And the implications of that. Plastics are absolutely hydrocarbons, right? Relating into organics. And if we can find some that biodegrade and have a significantly lower impact in terms of the environment, and that's a big deal. Anyway, things to consider, things to think about. Chemical engineering is certainly a super interesting area. Now, our focus on this first podcast is on addition reactions. And you had a very brief introduction to addition reactions when we talked last week about the bromine test for alkenes and alkynes. In other words, for the unsaturated hydrocarbons. So that's where it first was mentioned, but now we're going to go into a whole lot more detail. All right, here we go. Now, ultimately, guys, the key thing with addition reactions is you're always going to be starting with an unsaturated hydrocarbon. And all I mean by that is you're starting with something that has a double or a triple bond. We're going to focus for the most part on double bonds, but the triple bonds would apply as well. And you can saturate them, which essentially means only single bonds will be present, through addition reactions. So you take an unsaturated hydrocarbon, add something else, and you end up with a singular product that does not have a double or triple bond. And it involves that large hydrocarbon added to quite a small molecule. I'll give you some examples that work really well. The first one that often is added is hydrogen. Now, when you think of hydrogen, it's like, okay, is that really so small? Is it just a single hydrogen atom? No, you got to go back and consider all of those diatomic molecules. There's lots of them. The acronym I've given you throughout the semester is Hofbrinkel. But I mean, there's a multiple of different ones you can use to help you remember this. Ultimately, though, there's hydrogen right at the beginning, which means that if you are adding hydrogen, you're adding H2 gas. The other thing that I will clarify with any of the reactions that we're talking about this week is there is no need for balancing. So I know that sounds strange. It's not that you can't balance these reactions, or they shouldn't be. It's just we're not going to be using them at this point for stoichiometric purposes. So ultimately, your goal is to correctly draw the reactants, to recognize what type of a reaction is taking place, and then to correctly predict, draw, and name the products, not to balance them. Okay, here we go. Check it out. We'll jump right into examples. Your most important task at this point is what I already mentioned, to correctly recognize the type of reaction, but also you got to draw these properly, guys. If you don't, we're going to have issues with predicting products. Ethene, we have a hydrocarbon with a double bond, and you can see the F, so we know that it's 2 carbons. So I'm going to write this one out a little bit bigger and a little more detailed than I usually do. We'll actually show the individual hydrogens coming off. And I'll do this a few times with the reactions so that you can really see what's happening. So here's our ethene, and we're adding hydrogen. Remember, like I mentioned, hydrogen is diatomic. So when you draw it, you need to show that we have one hydrogen bonded to another. Now, what's going to happen with something like this is these hydrogens are going to be added to the original ethene molecule. Sorry, I made that look like it's being added to the hydrogen. Going onto that carbon. And that double bond is going to break, allowing the hydrogens to bond to the carbon, because now the carbon will have an extra spot open to bond, if you will. So the key thing is we now draw one single bond between the carbons. It's not a double bond anymore. And then we have that new hydrogen put on there. The previous hydrogens are still there. It's not that they've disappeared. But you can visualize that here's a hydrogen, here's a hydrogen. Now they've been added, hence addition, to the ethene molecule, which of course changes it. It's no longer ethene. It now is single bonded, still has two carbons, 1, 2. This is ethane. There we go. Done and done. Your most simplistic addition reaction. Key thing for you to recognize what this is that you are dealing with an alkene or an alkane or alkyne being added to something else. When you see that, then it's like ding, 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 oh, addition. Okay, let's try another one. Check out this one. You can still have cyclohydrocarbons in here. This is a cyclopentene, which means we've got 5 carbons that have been bonded with one double bond present. So let's draw this thing first. Okay, there's our 5. And then I'm gonna put the double bond right here. So from here, it didn't really matter where I put the double bond. There's just one, it's just that'll be carbon 1. And that we're adding, pardon me, the hydrogen, it's honestly the exact same idea. When the double bond breaks, those carbons will now have an extra opening for something else to attach. So one hydrogen will go to either side. As a result, we're going to have something that looks like so. So we'll redraw our cyclopentane, but now it's no longer pentene. It's now going to be cyclopentane. And notice that double bond has broken, right? Double bond broken. One hydrogen has gone onto each of those carbons. Naming wise, it's no longer the ene. Instead, it is a cyclopentane. A-N-E ending. Dun, 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 dun. There we go. Now, both of those examples were an addition of hydrogen. What if we add something else? So we can add a halogen instead. And when we do that, we're going to produce an alkyl halide. So a hydrocarbon with a halogen some point on those carbons. Now, if you look at this, when we're adding here, I showed you in this original one that this is X. And X, when we think of organic chemistry, is representative of halogen. The halogens it possibly could be, so X could equal bromine, X could equal chlorine, X could equal fluorine, or X could equal iodine. It's going to be one of those 4. Which one isn't? That's going to just depend upon the question, of course. Same thing, you're adding to a structure that has a double bond, potentially a triple bond, but like I mentioned, we will focus on double bonds here. One of the halogens is going to go into one carbon when that bond breaks. The other halogen is going to go on the other carbon when that bond breaks. And then we end up with both of those attached to the hydrocarbon. Naming wise, well, you know how to name alkyl halides. That's from last week. We're going to follow the same thing. Okay, so watch what happens here. We'll go through this. We have cyclohexene, hex meaning 6. So we have a 6-carbon cyclic structure. And it is a hexene, so I'm going to put a double bond in. It's being added to chlorine, a diatomic molecule. We really have to be set about that, please. From there, one chlorine is going to go on one of the carbons where the bond will break. The other chlorine will go on the other carbon. And when you redraw this, of course, you're going to have to carefully rename it. But put your chlorines on, one chlorine here, one chlorine here. With these, there's no other different branches going off, so I can start my numbering right where the halogen is. 1, 2, 3, it would keep on going. We officially have 1 comma 2 dash. Always have that correct punctuation in there. There's 2 chlorines, so we need the di. Some of you are messing that up on your assignments. 2 of them, you need the di. 1, 2 dichloro. Don't forget the word cyclo. Common mistake. It is no longer hexene, it is hexane. 1, 2 dichloro cyclohexane. That double bond is broken. Used to have one there, now we're single. Okay, let's do another example where we're adding a halogen in. But1-ene. In this case, we need to specify where that double bond is because there's more than one possibility. It's sitting right after carbon number 1. Oopsies. CH2, CH, another CH2 for the third one, and CH3 for my third carbon, or for my fourth carbon. There's that double bond. Okay, plus iodine. Iodine again is diatomic, so there we go. This iodine, you're hopefully getting the idea of this, is going to move onto each separate carbon when that bond breaks. As a result, think of what happens. We have that CH2 still present, but now an iodine has been added on. It is now a single bond between carbons 1 and carbon 2. We still have a CH here, that hasn't changed, but added on again is an iodine there. The end of the molecule remains identical, CH2, CH3. That double bond is broken, and the iodine has moved onto the molecule. What do we have as a result? Well, the numbering again would start here, 1, 2, 3, 4. 2 iodines, specify where both of them are, 1 comma 2 dash diiodo. I know it sounds weird. Butane. You no longer need to specify where that double bond is because that's gone. Okay, it's unnecessary. All right, guys, that's our main focus here with adding hydrogen or adding a halogen. And just to recap with you from a review of last week, that test that we can do, right? It's an addition reaction that makes more sense now though, adding the halogen bromine, which lets you know if you're dealing with a saturated hydrocarbon or not. If you think back to last week, I told you bromine is that orangish kind of reddish brown color. And when you add it in, if an unsaturated hydrocarbon is present, it reacts. So that means that that orangey color disappears. So really quickly, just to do a simple one, just to make sure you see it, pent2-ene, we have CH3, CH double bonded, CH, CH2, CH3. There's our pent2-ene, and it's being added to bromine, that diatomic molecule. You can visualize this pretty quick. Hopefully this is starting to feel pretty easy. The double bond's going to break. Bromine is going to go on. We will then end up with, I have to write it below here, CH3, CH. The bromine is going to be attached there because the double bond was present between carbons 2 and 3. So the bromines are going to go on carbons 2 and carbon 3. And the last step is simply naming it. Okay, notice that you have, it's still 5 carbons long, but now we've got those bromines on carbons 2 and carbon 3, dibromo pentane. This has broken the bromine halogen bonds, which means when those break and they attach to what used to be an unsaturated hydrocarbon, the orange color has disappeared. Hence, a positive discernible test for the presence of an alkene. Vice versa, what if we took something that wasn't unsaturated, where instead it was saturated? Pentane looks as follows: CH3, CH2, 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 CH3. So here's our pentane. If I add bromine to that, well, cool, I can add it, but there's no double bonds to break so that it can attach. So honestly, we simply have no reaction. Nothing is noticed. Nothing is seen to occur. That means that the bromine stays intact and the orange color persists. It stays. Okay? Again, this is review. We talked about these bromine tests last week. Now the logic of why you get the answers that you do should make a little more sense. All right, couple different types of addition reactions I want to go through. Same idea all the way, but instead of just adding a halogen now, we're going to add a hydrogen halide. And all a hydrogen halide is this, hydrogen attached to one of the halogens. So for example, this could be HBr, HCl, HI, or HF, right? Those are your hydrogen halides, hydrogen bromide, hydrogen chloride, etc., etc., etc. We still end up forming here an alkyl halide. It just won't be one with two halogens on there, unless, of course, a halogen was already present in the original hydrocarbon. So same premise exactly. You're going to end up with the double bond breaking and the hydrogen going on one of the carbons and the halogen going the other. The big twist with this one, and it is a twist, is you could form isomers because there's different ways that this could attach. Sometimes you end up with a structurally identical molecule. Other times it's a slight variation. Whenever you get variations, it's really important that you are going to list, as in draw, every isomer you get, and you were going to name them. And this is something I'm going to be looking for in your assignment. If isomers could be made, you better add them in. I'll show you what I mean. Check out this example. We've got but1-ene. So but for 4, it has a double bond right after carbon number 1. So looks like so. Now we're adding this to hydrogen chloride, so to HCl. And at this point, you honestly just need to make a decision. Where's the chlorine going to go? Where's the hydrogen going to go? One scenario is the hydrogen is going to go on the first carbon and the chlorine is going to go on the second carbon. But there's an alternative scenario. What if the opposite happens? What if that hydrogen instead goes on the second carbon and the chlorine goes on the first carbon? Both possibilities are viable, and you need to show both possible structures, which will look different, just slightly, but still different, and which will have different names. That needs to be listed. So in the first scenario, which was your red one, we're going to end up with CH3, CH, CH2, CH3, and chlorine is coming off of carbon 2. In the second scenario, which is the green one, we're going to have our CH2 and chlorine's coming off of carbon 1. Then I add the extra hydrogen on the second one. Notice before it was just CH, now it's CH2. And again, CH2, CH3. So I did condense the hydrogens into the formula, but you still need to recognize that they're there and make sure you add them in. All right, name-wise, yeah, these are definitely different. The top one here, it is on carbon 2, so this is 2-chloro, still 4 carbons, butane. There's no double bond anymore. The one below, this is 1-chlorobutane. There it is. These folks are officially your isomers. And in this particular case, there are 2 possible isomers that could come up. Like I said, if isomers are a possibility, you absolutely must list, draw, name them all. Super important. I don't assume that there's going to be isomers. It really varies. It's a matter of taking the time to look and think about it. Look at this next one. Before we did but1-ene, now we're going to do but2-ene. So CH3, CH, there's your double bond after carbon 2. CH and CH3. And we're still going to add hydrogen chloride to this. Now, here's the deal. When I break that double bond and I put hydrogen on carbon, the second one going that direction, chlorine on the third one going that direction, imagine this. Numbering my halogen has to take precedence. So when I redraw this thing, we have CH3, CH2, I'm going to run out of room. CH, there's our chlorine that's been added on, and CH3. Now it's tempting to number from left to right, but no, you got to keep the number of the alkyl branch the lowest. So actually I have to start numbering to the right. So 1, 2, 3, 4. The name of this then is 2-chlorobutane. If I took this and I instead put the chlorine on this carbon and I put the hydrogen here, look what that is. I'll still end up with chlorine on a second carbon. It's just numbered the opposite way. So it will still be 2-chlorobutane. Hence, there are simply no isomers here. There's one possible product, and we already drew it. One last example of another type of addition reaction. We do something kind of cool here where we add water to a alkene or an alkyne, and that'll produce an alcohol, which is kind of cool. Don't forget that water, H2O, really can be written as HOH. So ultimately, we are adding to one carbon the hydrogen, and we are adding to the other carbon the hydroxyl group. Perfect, right? That hydroxyl group is what will make it into an alcohol, as you can see here. Do not lose track of that water, H2O, is HOH. Makes it a lot easier to see. As before, we could certainly have isomers. Why? Because that hydroxyl group could end up on a variety of carbons. And as you remember from last week, I hope, alcohols are named specifically to the location of the hydroxyl. You have to be specific. Check one out here. If we do pent-2-ene, so we have CH3, CH, this is a 5-carbon one, so CH, it's going after the second one. Here's our double bond. Continue with the CH, CH2 for the fourth, CH3 for that 5th carbon. Plus, I'm not going to write the water, even though it just says water is H2O. That's too confusing. Instead, split it up into HOH. From here then, that first time I do this, I'm going to put the hydrogen onto that second carbon, going from left to right, and I'm going to put the hydroxide onto that 3rd carbon. So now we have hydroxyl group on carbon 3. Look at the alternative. This time I'm going to take that hydroxyl group and put it on carbon 2. That changes things. Carbon 3 versus carbon 2 is distinctive. And I'm going to put that hydrogen, and it's going to go on carbon 3. We definitely have isomers again, guys. Okay, let's have a look at them. With my red one, hydroxyl was going onto carbon 3. So we have CH3, CH. It got an extra hydrogen, right? Look at the red one. So this is now CH2, CH, and my hydroxyl group is on there. Finishes the same, CH2, CH3. Vice versa with the green, the hydroxyl ended up on carbon 2. So in that case, CH3, CH, put the hydroxyl group on. This is no longer CH for the 3rd, it's CH2 because it got the extra hydrogen. CH2, CH3. Naming wise, the red one is going to be a 5-carbon alcohol, and the hydroxyl group is on carbon number 3. So remember with these, we go pentane, we get that AN, drop the E because there's not more than one hydroxyl, dash 3, because it's on carbon 3, dash OL, specifying the suffix that this is an alcohol. And going on to the second one below that, pentane remains the same, but now it's on carbon 2. Pentan-2-ol. Do we have isomers? Oh yeah, absolutely. What about a cyclo though, like this? Slight difference. Cyclopropene, so a 3-carbon cyclic type structure. I'm going to put the double bond here, and we're adding water. Well, once again, it splits up, so hydrogen would go on one, and the hydroxyl group would go on the other. Now, guys, ultimately, wherever that hydroxyl is when it comes to cyclos will simply be named carbon 1. It doesn't change. And we don't even have to specify where carbon 1 is. It's assumed if hydroxyl is there, that's carbon 1. So the name of this, we still have to say it's a cyclo. We still have to specify the 3 carbons, so the propan, but then it's just all. Cyclopropanol. No isomers to speak of. Okay. In terms of questions that I would like you to try with this, these first questions are actually more review than anything. It's practicing drawing, it's practicing naming different molecules. In terms of identifying reactions and drawing correct reactants and products and naming them, that's going to be done when we're finished all 3 reaction types. Reason being is one of the most important parts of this is you identifying between and differentiating between. And you can't do that when you only know one of them. So good review here, making sure you were right on track with the skill sets we built in the last 2 weeks. Do all of number 1 and all of number 2. And a reminder as well, we're going to have another Google Meet on Thursday, completely optional. But if you've got questions, clarifications, it'll be at 11 o'clock. Please feel free to join in. As always, you can ask me questions other ways too. Okay? No big deal. But there's that optional time. Talk to you soon.